Landslides are catastrophic in many parts of the world. It can cause severe direct and indirect damages, such as human casualties and social facility destruction. Because they can occur quickly and with little notice, it is difficult to be aware of where landslides occur. The most effective way to prevent landslide-induced damages is to know where the landslide-susceptible areas are. Various landslide susceptibility maps have been developed and widely used, mainly in European countries, Japan, and the Republic of Korea. This module discusses how landslide susceptibility maps are made and analyzed. A landslide susceptibility map takes into account where landslides occur and what causes them. The term susceptibility should not be confused with the terms hazard and risk. Landslide susceptibility is a function of the probability of landslide occurrence and landslide-related factors. Slope, soil type, and the impact of the flow of water in an area. It does not depend on influencing factors such as rainfall, earthquakes, and human activity. The term landslide hazard, on the other hand, depends on susceptibility and influencing factors. The term landslide risk is estimated from the hazard and the presence of vulnerable target, such as people and property. A landslide susceptibility map identifies areas predisposed to landslides. It provides the spatial distribution of landslide occurrence within a given territory. Such maps are developed or implemented by agencies, local, national governing bodies, as they evaluate various land use. Their main purpose in using susceptibility maps, therefore, is not to predict landslides, but rather to reduce the risk of landslide hazards when using specific tracts of land. Accurate and reliable data are essential to develop the susceptibility map because mapping is a site-specific and data-dependent process. Thus, data collection is the main step in landslide susceptibility mapping. The necessary data are obtained from various sources, such as field survey, aerial photography, or remote sensing images. Based on historical inventory, landslide polygons are extracted and converted to raster data or vector data. Traditionally, natural hazard assessment and mapping are laborious tasks, requiring enormous time and effort to manually handle and process data. However, the advent of a Geographic Information System, or GIS technology, facilitated easier handling, processing, analyzing, and reporting of data. GIS is a computer system that analyzes and displays various information alongside its geolocation. Use of GIS-based landslide susceptibility mapping has increased rapidly in recent years, and is now the main tool used to define landslide vulnerable areas. Data collected are divided into qualitative and quantitative variables. Qualitative variables such as land use and land cover type are resampled to have 5 to 10 categories. Quantitative data are grouped into several subclasses. For example, elevation data extracted from Digital Elevation Model, DEM, is simply reclassified into a 200-meter interval. The number of classes depends on the range of data available, but 5 to 10 classes are commonly used. Many models have been used to evaluate the functional relationship between the influencing factors and existing landslide events. They can be classified into qualitative and quantitative approaches. Qualitative approaches are based on past experiences or professional judgment and are more subjective than quantitative approaches. Quantitative approaches closely rely on statistical results, which have much less personal bias. Quantitative approaches could even be applied to regions that haven't experienced any landslides, but could very well be landslide vulnerable. The advantage of a quantitative approach is that it can be applied over a large area, and the ratings for various factor classes can be deduced statistically from past landslide data. However, the limitation of quantitative approaches is that they do not propose mechanisms to prevent slope failure. Rather, it assumes that future landslides can be predicted based on past landslide occurrence. Quantitative approaches can be bivariate or multivariate. Bivariate analysis involves the analysis of two variables, often denoted as x and y, for determining the statistical relationship. Here, the values are assigned based on statistical relationship between past landslide density and various influencing factors in each individual class of every factors. The widely used methods for bivariate analysis are frequency ratio method, statistical index method, weight of evidence method, and certainty factor method. Multivariate analysis determines weighting factor of interrelationships among influencing factors. After sampling all relevant aspects at appropriate scales, the presence or absence of landslides is determined. A landslide susceptibility and hazard zonation made through a multivariate statistical approach is based on the relationship of the relative contribution of each of the influencing factors to the total landslide susceptibility in the area. A multivariate analysis determines the percentage of landslides for each pixel. And through statistical analysis, the data layer on landslide presence or absence is developed. The commonly used multivariate statistical methods for landslide susceptibility and hazard zonation are the logistic regression method and multiple regression method. A landslide susceptibility map will not be useful without a reliable validation. Validation is an important step to test the predictive capability of a landslide susceptibility map. A landslide susceptibility map is typically constructed using 80% of the data. This model is then validated using the remaining 20%. There are various types of validation techniques for landslide susceptibility maps, such as area under the curve, AUC, and landslide density index, LDI. A receiver operating characteristic, or ROC curve, is a graph used in data science to show if the map created is accurate or not. Similar to other countries, the Korea Forest Service, KFS, developed the National-Wide Landslide Susceptibility Mapping System a few decades ago and have updated in 2020. Based on the weighted values for 9 influencing factors, a national-wide logistic regression analysis was adopted to score the influence of triggering factors on landslide occurrence. The 9 major landslide causative factors included slope gradient, slope length, slope aspect, profile curvature, lithology, bedrock, soil depth, forest type, forest age, and TWI, topographic wetness index. The triggering factors, including rainfall, earthquake, and volcanic eruption, are usually not considered when generating landslide susceptibility maps. The influence of topography is reflected in slope gradient, slope length, slope aspect, profile curvature, and TWI. These geomorphometric output values were generated from DEM data. Slope gradient is the elevation over a measured distance. Landslide occurs more frequently on steeper slopes due to gravity. Slope aspect refers to the slope orientation and influences exposure to sunlight, wind, and soil saturation. Slope aspect was divided into 8 classes for developing the susceptibility map. Profile curvature affects the driving and resisting stresses within a landslide in the direction of motion. The remainder, TWI, indicates the spatial distribution of soil moisture and surface saturation. Lithology, the general physical characteristics of rocks, is another influencing geological factor in slope stability. Each bedrock material has a different shear strength and permeability characteristics. Different rock types have varied composition and structure, which contribute to the strength of the slope material in a positive or negative way. Stronger rock units give more resistance to the driving forces as compared to the softer or weaker rocks. 5 main types of rocks, such as sedimentary, phyllite, gneiss, igneous, and volcanic rocks, were derived from the existing National Geological Map and used. Data on soil depth or soil thickness were extracted from the forest soil map. Forest type and age are important factors to represent the influence of land use and land cover. In order to build the regression model, forest type was divided into deciduous, coniferous, and mixed forests. And age distribution of forest stands was grouped with 10-year age classes. The forest information was extracted from the forest cover map in the entire country. The additional effects of electric transmission tower, forest road, and forest fire damage were subjectively considered, based on expert judgment. The recently released system in the Republic of Korea classifies the probability of a landslide into 5 classes for the forest lands of the entire country. Class 1 is very high risk. Class 5 is very low risk. Usually, areas that are Class 1 and 2 are legally restricted for any use, or permitted only with appropriate countermeasures. The Landslide Susceptibility Map, embedded in the Landslides Information System, LIS, in KFS, is available in digital format to be viewed online under the integrated GIS system. The LIS is used in various forest utilization, protection, and management sectors. For example, LIS identifies the most prone area for landslide occurrence during intense rainfall or typhoon. National and local governments can assess LIS to examine the potential of landslide occurrence for a specific area.